Thank you very much, Claire, and thank you to the organizers for inviting me over. So my talk has a few things in store, but I'm going to be focusing on thermal energy storage today, and mainly from a technological perspective. Before I dig in, I want to say very quickly that up until yesterday morning, I was in Mauritius for something called a Royal Society DFID Africa Capacity Building Initiative project. This is a 15 million pound set of 10 projects. In our case, we're focusing on CSP, concentrated solar power. The reason I'm mentioning this is because while I was there for a series of meetings with local industry, I heard on Monday or Tuesday last week that there was a cyclone headed our way. And I was incredibly lax for a few days. I thought that something like this was approaching the island. It turns out that something like that was approaching the island. This is the whole island of Mauritius. At which point, when I realized this was Wednesday or Thursday, I sent a frantic email to the organizers to say I wasn't quite sure I was going to make it out of this. But anyway, so I am delighted to be here, literally. I escaped this. And now I'm going to start my talk. And really what I want to try to do is just make a few points, and then hopefully at the end, maybe I'll convince you that some of these points make some sense and you need to remember them when you're thinking about energy and storage. So anybody who works in the thermal area and comes to an energy storage meeting is fighting an uphill battle. First of all, you have to convince people to stop equating energy with electricity. There are other forms of energy that we want to try to keep in the mix. And of course, the corollary of this is that energy storage is not only electricity storage. Okay. The other thing I want to say is that many people talk about thermal energy storage, and we tend to think of heat because we live in a country where most of the thermal demand is wanting to heat homes and so on. But there's also cold energy and a so-called cold chain, and that's also very important. And I'll talk briefly about one of each of these two. So I'll present some examples of technologies where we use hot and cold. And heating and cooling is very important, and in the context of the UK, we need to remember that over 50% of the final consumption of energy is basically due to heating and cooling and not electricity. So it's a very important thing to remember. So now going to thermal energy storage, this is a bit of a definition. So thermal energy storage relies on changes of internal energy. And again, I want to try to convince you through what I'm going to show, various options and technologies that you can store heat, for example, with thermal energy storage solutions, but you can also store electricity, but you have to convert your electricity first to some heat or cold that you store, and then you have to convert back to electricity, and we do have technologies that do this. So thermal energy storage can be used for electricity storage as well. One very quick thought, and we've been hearing a lot about this, is that there is a push to electrify heat, and there's a push to electrify transport, and we've been talking about electric vehicles. This is the final consumption of electricity in the UK. This block here is electricity at the moment. This block here is mostly because of heating at homes, and this block here is transport, so this is final energy use. And I think one of the big challenges that we face is if we want to start doing all of this electrification, the obvious thing that we need to think about is how we're going to increase electricity generation and consumption by a factor of 3 to 4. And this is not a trivial thing to do. So thermal energy is a big part and fuels are a big part of our final energy consumption. It's not easy to just say everything will just become electric vehicles and the whole grid will just become heat pumps and we'll just use renewable electricity. Anyway. Okay, so what is thermal energy storage? Well, you're sort of familiar with the basics of this. Most of you might have a hot water cylinder in your household where water is stored at some temperature. There are larger versions of this that you can find. So this is one in London, this is one in Austria, a bit larger than the one in your household, but it's the same principle. We can store hot water. We can store steam at pressure. So this is another way of storing thermal energy. We go to higher temperatures and pressures typically than if we're storing hot water. So these are sort of conventional solutions that have been around for a very long time. And other solutions that have been around for a very long time are in CSP plants. So this is just an example of one where we're trying to hybridize CSP with biomass, but that's beside the point. You'll often find these days as a standard, anything between 4 and 12 hours of storage, and that's done through molten salts. Okay, and the molten salts are also used as heat transfer fluids inside the collector fields. Okay, in this case, you're passing the salt directly through the solar field. In other cases, you can have indirect flows where you sort of have a heat exchanger and you store heat that way. But these are things that have been around for a little while. Where do they fit in the big picture? So this is a very nice plot that I like. It's taken from this reference, but it has been updated, and it's been updated by a colleague of mine called Yulong Ding, and I'd like to acknowledge his contribution here. So what this does is it shows energy density on this chart here. It's logarithmic, so we need to be very careful with that. We go up 1 order of magnitude for each one of these lines, and this is the temperature at which we store heat. And the main thing that I wanted to say here is that the options which are available to us are from water, so this is basically us heating water up and down, yes, so classical solutions. We can go to things like called phase change materials, so then we start to use the latent enthalpy of phase change. We can have sorption and we can have chemical reactions, and each time we go from one of these to the next, what tends to happen, you will find, is you go up on this scale of energy density. Now, that's a very good thing, so you want to have as high energy density as possible. You also go up in cost, though, and this is a problem, and we'll come back to this a little bit later. So you're not going to beat water in terms of some sort of volume, but you might get close if you consider the fact that other things require smaller volumes, although this is not as trivial, and I'll show you some examples of this later. I'm not going to talk about chemical reactions, and also I should have said these solutions out here are lower TRL, so I won't focus on those. The speaker before me did an excellent job. I will more focus on phase change materials. What isn't evident on this chart is that we don't only store sensible energy in water. There are all sorts of other things that we can store heat in, so we can use gravel, we can use the soil, interseasonal storage, we can store in ponds, concrete, tanks, whatever we want. Okay. So let's look at phase change materials a little bit more carefully. Here we have another breakdown from this reference where we go sensible, latent, so this is PCMs, these phase change materials, chemical I won't speak about, and of course if you have phase change, then you can have any combination of gas, liquid, liquid, solid, and back, and so on. But really what I want to make the point here is just to give you a feeling of what we're talking about is that typically 2 classes of substances which are used. They're either organics, and those can be things like eutectics, paraffins, fatty acids, and so on, or the other big category are inorganic. So there we start having things like salts and so on. And there's a big range of, a big temperature range, and they tend to be used in slightly different areas, so organics are not really very good for very high temperature applications. This is obvious. Okay? There's a lot of work in all of these materials because they have their role to play in different applications. In some cases, cost is more important, safety, in other cases, space is very important, so you need very high energy densities and so on. Now, one of the things about thermal energy storage that I made the point very early on to try to convince you about is that thermal energy storage can be used to store heat. Okay, that kind of makes sense. So if I want to use heat as heat, I can store it and then use it later. But it can be used also for storing electricity as a sort of intermediary. And I'm going to try to convince you that this is possible. So first of all, this is a chart which shows for how long we might want to store with different types of applications, all the way from energy management. This is in the context of electricity storage now, down to power management. So energy management typically are sort of minutes and above, hours, weeks, and so on. And so thermal energy, and this thing here is basically the wattage, so the power of a particular application for energy storage. So thermal energy storage would occupy this space over here. It's good for energy management. It's not very good for power applications. So you're talking about devices that are where you're able to put heat in and out of something not faster than of the order of a few seconds, tens of seconds, minutes, hours, and so on. So it's not very good for fast processes. Okay. But on the other hand, it's actually very good on scaling in terms of power. So down here of the order of kilowatts or tens of kilowatts would be a simple tank of water. That would be a few kilowatts or tens of kilowatts, depends on the size, of course. but you can have very large systems, and I showed you systems where the tanks are massive, or you can store underground in aquifers and so on. So there is a big span on the horizontal axis here. So now I'm homing into a couple of interesting technologies that I wanted to talk to you about. And I'm specifically interested in large-scale electricity storage. Maybe I shouldn't be saying this, but personally I'm not a believer in thermal energy storage in the context of electricity storage in small systems. So batteries are probably going to win that battle. But if we look at things like, and I think of all of these, I would maybe just concentrate on this one, on this chart over here. If we look at systems where we want to have long discharge times, so we want to store, say, electricity over long times. Heat is very good because you can store heat over long times relatively easily, as long as you can minimize those thermal losses. And if we look at rated powers which are large, so we're talking about large systems, tens, hundreds of megawatts, hours, and upwards, then the sort of things that come out of these charts are technologies like pumped hydro. Okay, we know that, we have it, that's great. Compressed air, a bit newer. And then we have two technologies that I want to tell you about today. I'm not going to tell you about compressed air, but I will tell you about something called liquid air energy storage, because the UK is playing a key role in the development of this technology. And I want to tell you about pumped thermal electricity storage, because the UK is also playing a role in the development of this technology. And these are earlier stage technologies which we should keep an eye out for. So where would they lie? Well, the answer to that kind of depends. The boxes on this diagram overlap what they overlap, because that's where we said we might be able to design a system. It doesn't mean that you can't, let's say, have thermal reservoirs which store for even longer. It's just an engineering challenge. That's where we sort of thought we would do our little study that I'll show you some results about later. But again, to give you this idea that we're on the sort of top right-hand side of this chart. Okay. So what are these technologies? Let's go to pumped thermal electricity storage first. Pumped thermal electricity storage is basically what it says on the tin. Okay, so what happens is when you have electricity, there are four components here. And effectively, when you have electricity, you run a heat pump. And what does a heat pump do? It takes heat from something cold and it delivers it to something hot. So we have a hot reservoir here that we charge. So this is heat being pumped into here. And we have a cold reservoir over here, which of course we're removing heat from. So the gravel there, and this is a packed bed. So the gravel there gets very cold, minus 150, or it depends on your design. Okay. And of course, in order to drive this system, we need a compressor and expander. Okay, and there's a UK company, was a UK company. We can discuss this a little bit later. They now no longer exist, but they had a very interesting idea for how you could design these compression and expansion devices, and they had all sorts of other ideas as well, but they ran out of funding. Anyway, this is the pumped thermal electricity storage system, and this is now been so they've declared bankruptcy, and their facilities are now owned by the University of Newcastle. And you can go to this website and read about it. But effectively, there is an effort now to get this pilot plant, which is a 1 to 2 megawatt pilot plant, up and running. Okay, and these are the hot and cold stores. So this is where you store the heat. These are the sort of packed beds that I spoke to you about, and this is their very interesting compressor and expander with all sorts of very nice innovative ideas that go into pretty much all of those components. And if I may be allowed a personal opinion on this, there's a lot of innovation in this technology, and one of the decisions that Isentropic made early on was effectively that every single component here is designed and manufactured from scratch. Okay, so they're going for high performance components, and that's always difficult to deliver because you have challenges everywhere. There are very few off-the-shelf components here. I wanted to very quickly go outside of these compressor expander components. This is just another diagram that you can find on the web. I gave you the web address, but the other interesting idea that Isentropic had was about segmenting their stores. And there are some advantages to that, but there are also some disadvantages to this. And in the end, I'm not entirely sure which one of those two is going to win over. But so there are lots of interesting ideas that go into why you might want to do something like this. But again, just to summarize, This is a UK-led effort. It is still ongoing. At the moment, we're at the stage where the University of Newcastle is trying to get this thing to turn over. Okay, so this is a first-of-a-kind pilot plant, and this we'll hopefully get some data on that. What does it look like? So this is our pumped thermal electricity storage. These are some numbers. You can have a look in the literature. This is pumped hydro compressed air, and the one thing that you'll immediately notice is that it's actually pretty good in terms of energy density compared to things that we are more comfortable and familiar with, so pumped hydro and compressed air. So that's one case where we're storing electricity in the form of heat and then getting the heat back. Another thing we could do is store electricity in the form of cold, and in this case what we do is we run a liquefaction process and we liquefy air. We can store the air at ambient pressure, okay, and then when we need it back, we can discharge it and run a power cycle, a turbine. There are various variants on this and using waste heat to improve performance and so on. You can go to the website of a company called Highview Power, and they have all sorts of interesting information and nice diagrams about how you can run these systems. So liquid air energy storage is one step ahead of pumped heat energy storage in the sense that they have a pilot plant, and that pilot plant is already operational. Okay, another megawatt scale, 5 megawatt, I think, design pilot plant. And this is very important for us because we begin to get some kind of confidence in our models of how we can predict the performance of these technologies. So pilot plants are very, very important in providing us with that level of confidence that some of the models are doing a decent job in capturing things like the round-trip efficiency of these technologies, things like what is the ultimate energy and power density, and so on. And I wanted to just sort of throw this in there. This is not an energy storage technology, but it's very much related to solutions where you have liquid air available. Okay, and this is something called the Dearman engine. For those of you who haven't heard about it, it's a so-called combined heat and power solution. Dearman Engine, another UK-based company, is just doing great work on taking that liquid air and effectively finding solutions by which you have now cooling that you can supply, but you can also expand liquid air in engines like this and generate power. Okay. One particular application that they're interested in, they're working very closely with Sainsbury's, and I can tell you more about that, but they could probably tell you even more than I can. Is on trucks, refrigeration trucks. Okay, so this is a very nice application where you have typical refrigeration systems are extremely inefficient. Okay, and so this solution can actually outperform typical refrigeration systems on board in automotive applications and generate some power. Okay, so very quickly, just to tell you where we are with things like cost compared to things that we might feel a bit more comfortable with again. Batteries is a bit of a catch-all term for lots of different technologies, but storing electricity is actually very expensive, and it's difficult to do, and you can appreciate that. But storing heat, for example, using molten salts is much cheaper, so an order of magnitude cheaper. And this is watt per watt for watt. Okay, so this is not per unit watt thermal, this is per unit watt electrical. Okay, in the context of CSP. So we have an interest in thermal energy storage because there are some cases where it actually makes more sense, okay, storing the heat and then converting back to electricity than, say, storing the electricity directly. These are some comparisons between liquid air and pumped thermal energy storage. Some are per unit power, some are per unit energy. The main I think lesson or conclusion from some of these costing analyses is that, yes, maybe liquid air has a slight advantage over pumped thermal, not so much in terms of levelized production costs as per unit energy kilowatt hours, but more in terms of power, capital cost. Of course, there are very large uncertainties with this, and we don't actually have an operational plan, so it's difficult to actually, with confidence, say what these costs are going to be. But this is what it's looking like, and those are other solutions you might want to compare it to. So it's not a million, especially liquid air, it's not a million miles away from other things. The final thing I wanted to show is buy-to-sell price ratio. So this is actually very important if you're trying to make a profit by buying electricity cheap and selling it at a different time when it's more expensive. And these lines here are lines which basically tell us where the NPV of some project breaks even, so when it becomes zero. Basically, anything higher than this, you start getting a profit, and anything lower than this, there's no point in going into a project like that. Okay, and they're actually pretty much tied on this also in context of given the errors that we have. Okay, so some very, very quick thoughts. This is, as many people said, a molecules to systems problem. Okay, the actual system we're dealing with is very complex, dynamic, and involves all sorts of things. But actually, there's a lot of research that's going on into new materials, extending the temperature capabilities, extending the energies and power densities, and so on. There's a lot of interest in how we maximize the use of these materials within certain devices in order to have a benefit at this large system level over here. And very quickly, from a material perspective, so going down to the molecules, of course, what do we want? Yes, we want high energy and power densities. There's a lot of research going on in these areas. We want long lifetimes, lots of cycles. Thermal energy storage is typically good for this. We want a wide range of temperatures, and we want to try to understand links between what structure the material has to have and its thermal properties. This is very important. One problem is that you're not going to get very far in these types of areas by just looking at the material itself. And one thing, maybe I'll skip in the interest of time. So one thing that you will find, for example, is that phase change materials are excellent if you just look at them from a bulk material property perspective. So you can store a lot of heat, say compared to water per unit volume, but they're not very good in terms of thermal conductivity. It's actually quite difficult to get heat in and out of phase change materials. And I'm showing you here cases where we were trying, so we had 2 tanks, one full of water and one full of a phase change material, and we're trying to get heat in and out of these tanks. And you can see here how much better water does, right? So the higher you are on this chart, how much better water does than a phase change material. Ultimately, what this really means is that you're not utilizing, it's very difficult to utilize this volume of phase change material that you have because you have to wait for the heat to go in and come out. Okay, and so I wasn't going to talk about all this, but really just to point out that there's a lot of work in trying to then harness, right, these good material properties that these materials have by careful heat exchanger designing the device, and how do you get heat in and out. And this is an engineering, sort of practical thermal engineering problem rather than materials now. Okay, so there are challenges at the process and component side. We want the processes and the components to be scalable, efficient. We want to have intensified processes. We want to try to get heat in and out of these. It's not just good enough to have a high energy density material. And of course, we need to try to understand how these components operate within systems. And a couple of examples of this very quickly, I'll just go quickly through these, are some solar distributed power generation applications. So here we have one based on something called hybrid photovoltaic systems. Hybrid photovoltaic systems are basically a PV with some thermal stack in there as well. So you're generating electricity and heat at the same time, a bit like a solar thermal plus PV hybrid. And of course, you can store electricity and you can store heat. And I'll show you some interesting sort of system level assessments that we've done and what it looks like. And of course, you're catering to the demand of some household. So there are time-varying demands as well for electricity and heat and so on. Another one is based on purely solar thermal solutions. So here we have a solar array of conventional solar thermal collectors, and we have some kind of power generation system, which is small scale, and this is suitable for distributed power generation, okay? Based on something called organic Rankine cycles, which I won't go into details of, but you can see I'm pointing at components within these systems where you're doing some kind of thermal energy storage. So here there might be some kind of phase change material. Here it's a steam accumulator, but not for steam, but for the organic vapor. And various variants of this, again, I'm pointing at the storage items. So here what you would do, for example, is you'd run your simulations. Over the course of a day, something gets charged, and then at some time in the evening, you have a control algorithm, right, that then runs the power generation part separately because you want to turn your kettle on, right? So it decouples the generation part from the collection of solar energy apart from the generation. And if you run it over much more complicated time periods, weeks, months, and so on, then the picture is much more complicated, and you start getting a feeling for how big do these tanks need to be, the cost, and what is the value of thermal energy storage in these systems. This is my last slide. So you can go from things like covering 3% of a household's demand in cooling, if you have a cooling part of the system, to covering 40% of the household's demand in cooling. So this is what thermal energy storage allows you to do, and it has to be done at cost. Okay, so I want to summarize. So I hope I've convinced you of everything which is on red on this slide. So I hope I've convinced you that, yes, there are thermal aspects here, not to forget about that, that we do have hot and cold, that the UK has a leading role in some of these technologies, okay? And that, yes, I think with that I've come to the end of my talk. Thank you very much.